All right. Good morning or good afternoon, everyone. We're doing the second lab session for our reports. It's our third lab report. Y'all are going to be working on your aggregates currently, but this is the second portion of material we're going to be learning, and we'll be covering the hot mix asphalt. So it's a three-part lab. We've broken it up into different sections for y'all. So the first one, we typically would do a NCAT binder lab tour, and then we'll go through and learn about the rotational viscometer, which is important for your report. And then you want to, and then what we'll do is we'll go and we'll batch our aggregates. So the next week after that, we'll look at mixing binder and aggregates. Then we'll compact asphalt concrete samples. And then the third week, we'll do our RICE test, which will get our maximum theoretical specific gravity. And then we'll do bulking, which is where we get our volumetrics. Y'all have probably seen that in class, our VMA, VFA, all that stuff. And you can get your bulk specific gravity of your asphalt concrete. So next slide is a video. If there's a problem with it, if it looks really stuttery, let me know, and I'll fix that for us real quick. But this is just an introduction of the NCAT facility, not the binder lab tour just yet. This is a little 3-minute intro to what NCAT is and what NCAT does. So we'll go ahead and do that. Send me a message if it looks bad, and I'll get that sorted out.
America relies on our highway infrastructure. For over 3 decades, our National Center for Asphalt Technology at Auburn University has focused on improving our roadways by evaluating and developing new technologies to make our roads smoother, quieter, safer, longer lasting, and more economical. NCAT was established through a partnership between Auburn University and the National Asphalt Pavement Association. We take pride in our strong relationships with state transportation departments, contractors, and others involved in the asphalt pavement industry. We strive to provide practical research results that are relevant and implementable into practice. Our highly qualified engineers understand pavement performance every step of the way, from the laboratory to the field. We are also developing the next generation of industry leaders. Students have the opportunity to obtain practical research experience, and many former NCAT Road Scholars are now in key infrastructure positions around the world. The NCAT test track is the only facility that combines real-world pavement construction with accelerated loading using heavy truck traffic. Highway agencies and industry sponsors fund research on the 1.7-mile oval, where our fleet applies over a decade of interstate-type traffic in only 2 years. Structural test sections have embedded strain and pressure sensors to measure pavement response to loads for validation of mechanistic empirical design procedures. Performance is monitored on a continuous basis to evaluate rutting, cracking, texture, friction, and noise. NCAT is at the forefront of pavement preservation research to quantify the life-extending benefits of various treatments and treatment combinations at test sections on and off the track. Our AASHTO accredited laboratory is well equipped to provide independent testing and analysis to help ensure that our roads are durable and keep drivers safe. People from around the world reach out to NCAT for assistance. We offer a wide range of hands-on training and can customize workshops to meet your specific needs. Asphalt is the most recycled material in America, and decades of research at NCAT have improved the sustainability of asphalt pavements. NCAT engineers are also using breakthrough materials and concepts to refine asphalt pavement designs, such as perpetual pavements and porous friction courses, which can enhance the quality of stormwater runoff while improving driving safety. Integrity is at the core of everything we do, and our research results are recognized worldwide as credible and objective. This gives our sponsors the confidence to move solutions into practice, saving highway agencies millions of dollars each year. Our mission at NCAT is to provide innovative, relevant, and implementable research, technology development, and education that advances safe, durable, and sustainable asphalt pavements.
All right, so our next video is the binder lab tour that Pamela did for us. So it just gives some insight into some of the different tests we can do in the binder lab. I know y'all have gone through some of those in the class handouts and lectures. This will just give you a video of like what's going on, and she'll talk through a few things pretty briefly, and she'll go through everything that's in her lab she's over.
Okay, welcome to the NCAT binder lab. We're going to do just a quick walkthrough and point out all the major pieces of equipment that you should have seen in class so far. We're going to start with this guy. This is our penetration device. This is our first official asphalt test. It is ASTM D5, and to give you a frame of reference on that, our dynamic shear rheometer, which we'll talk about in a minute, is about a 20-year-old test method, and it is ASTM D7175. So this guy is old. It was developed in the late 1800s by Mr. Bowen of the Barber Asphalt Company. And by first official test, I mean it was the first test that had a specified temperature, time, and loading rate associated with it. And why that's important is everybody's running it the same way. We don't have any personal biases to it. We don't have any tweaks. So I can run it in my lab and somebody else can run it in their lab and should get the same results or something that we can compare. Whereas if I'm running at 25, somebody else is running at 30 Celsius, someone's running at 35 Celsius, then we cannot compare our results because they're not run the same way. But it's a very simple test. We take a 3-ounce tin full of asphalt binder. I condition it in a water bath at 25°C for an hour. I'll scoop it out in a cup, set it up here on the platform. I have a big, long, wicked-looking needle that I will attach to the device. And I can't actually run this because I don't have it set up because you can't see it with the water bath. But I will set the tip of this needle on the surface of the asphalt, and I will let this fall for 5 seconds. There it goes. And then I can push down on the dial gauge and get my penetration reading. 1 pin unit is 1/10 of a millimeter. So this is basically telling me how far this needle is penetrating into the surface of the sample. Softer the asphalt binder, obviously the larger the penetration number. Stiffer binders have smaller numbers. Okay, so we saw the penetration device. It was a very simple piece of equipment. This is the dynamic shear rheometer. This is the backbone of our current super pave testing system. To get a PG grade, a 64-22, a 76-34, whatever we're testing, we will run this test 3 separate times. We do it on the unaged binder straight out of the tank. We'll do it on our short-term aged binder from the rolling thin film oven. And we'll do it a final time on the long-term aged binder out of the pressure aging vessel. This is a parallel plate rheometer, so my sample is sandwiched in between the 2 plates. The bottom plate is stationary, the top plate oscillates back and forth in a sinusoidal load. Speed is 10 radians per second, that is equivalent to 60 mile per hour highway traffic. Temperature ranges will go from 88 Celsius, we can go down to 4 Celsius. This is a sample. We use the little silicone molds. That's my 25 millimeter sample. This is the bending beam rheometer. This is our low temperature test. So when we get a PG grade of like a -22 or a -28, that result comes from this test. This is a Canon thermoelectric bending beam. We take a long-term aged binder and we mold it into a beam like this. It goes in the test bath at 10 degrees warmer than our low temperature grade. So this is a -22 binder. I will test it at -12 Celsius. And it stays there for an hour. After that hour, I'll place the beam on the sample supports. And the test is just a simply supported beam with a point force in the middle. We apply a 980 millinewton load to the middle of that beam for 4 minutes, and we measure how it deflects. We can see that on the graph right here. The top is my deflection curve, and it's doing exactly what we want it to do at cold temperatures. We want the beams to bend. That means they're not going to break as quickly. And then down here on the bottom, this is my testing load, and obviously I want that to be perfectly flat because this is a creep load, not a dynamic load. We are looking for this particular test, we're going to try to make sure that at 60 seconds of this 4-minute test, that we are not too stiff to handle the cold temperatures. We've got a maximum requirement on our stiffness. And then we're also looking at the slope of the stiffness versus time curve. We want it to be at least 30%. That will tell us that at really cold temperatures, the beams can handle the movement of the pavement with the dropping temperature, and they're not going to be brittle enough that they're going to break. When we're testing our asphalt binders for the super paved grading system, we have got 3 aging conditions that we talk about. We talk about unaged, which is the binder that's straight out of the tank. Our binders don't stay in the unaged condition very long because we send them through the mix plant and we start aging them. So we're really not terribly worried about the unaged condition. We have short-term aging. This is the rolling thin film oven. This is our short-term aging device. It simulates what happens to the asphalt binder as it goes through a mix plant. So rolling heat and air, just like the binder experiences during the mixing process. We'll take glass bottles like so. They hold 35 grams of unaged binder. We'll turn them on the sides, let the binder coat the sides of the bottle, set it on the counter and let it cool for 1 to 3 hours. That's just so that when I start the test, all of my bottles have the same stiffness. So I've not got a bottle that's really still hot because I just poured it and a bottle that I poured 5 minutes ago that started to cool down. They're going to roll differently. So I want everything to be the same stiffness when I start. But when I'm ready to run the test, I will put my bottles. This carriage here holds 8 bottles. I'll throw the bottles in here. I will let them spin at 15 RPM. For 85 minutes at 163 Celsius. That 163 Celsius is kind of an average mixing temperature. As the bottles are turning, the binder is rolling around in the bottle, and then this cobra looking thing right here, this is an air jet. So every time the bottle goes past it, it gets a nice poof of hot air, just like the mix plant. So when the binders come out of here, they are the equivalent of a newly compacted pavement. We will take the bottles, we will scrape them into a can, recombine them. I'll take a little tiny sample for the dynamic shear rheometer test, and the bulk of this will just go on into my long-term aging procedure. The other thing that we get out of this is something called mass change. So of these 8 bottles, 2 of them I'll handle a little bit differently. I will weigh them out to 3 decimal places before the test. I'll weigh them again after the test, and I will calculate what percent of the binder that we lost during this aging process. We are allowed a maximum of 1% mass loss in our super pave system, and that's just to make sure we don't have a lot of smoke and fumes billowing off the mix plants, because that's bad for the environment, it's bad for the workers, the neighbors get to wanting to call the EPA when they see that happening. This is the pressure aging vessel. This is our long-term aging test. So after we have run the rolling thin film oven, we've got our little sample for the DSR, we've weighed our mass change bottles. Most of the material that comes out of that aging procedure goes straight into this one. This is a long-term aging. It is 7 to 10 years of pavement life. It is a 20-hour procedure, so we set it up to run overnight. But the way it works, we will take flat pans with 50 grams of our RTFO-H binder in them. I've got a rack right here that will hold 9 of these. I will place this in the chamber, close the lid, big bolts that hold the lid on for me. Once everything is in place and it has reached my pressurizing temperature, I will apply 300 psi of pressure, and that's when those bolts come in handy, because if the bolts fail, the lid is going to go through the roof. And I will let it sit for 20 hours and come back the next day and take it out. Aging temperatures, typically it's 100 degrees Celsius. If I've got a really soft material, it's going to be used way up north, I'll go down to 90. If I've got a material that I'm going to use out in the desert, I have the option of 110. But typically everything we do here is 100 degrees Celsius. After 20 hours, we'll take everything back out. And they will look like this. So we've got a lot of air bubbles in here. I'll combine this back into a pan, pull a vacuum on it to get the air bubbles out, and then this is the material that I will use for my bending beam rheometer and my long-term age dynamic shear rheometer. The reason that we long-term age things is so for our cracking tests, we can differentiate between binders. If I tried to run the bending beam rheometer or my DSR cracking test on an unaged binder, everything's going to look really, really good. But once I have run it through here, I've got 7 to 10 years of age on it. Now we're going to start to see differences between binders that behave well for cracking and binders that behave poorly for cracking. This is the flashpoint test. This is the safety and handling test in the SuperPave grading system. And actually this test has been in every grading system that we've had for asphalt binders since we started developing grading systems. It basically tells us how hot can we heat the asphalt binder without it actually catching on fire. And that's good for out on the road, somebody drops a cigarette, or if you get a spark off a tanker door or something, you don't want to have an explosion, hurt people. So the way we do this is we'll fill this up with asphalt binder, place it on here. We will heat this up at a prescribed rate. I've got a little flame on the end of this guy, and I will pass this over the top of the sample of binder. And I've got a thermometer that will be suspended down in here. I will pass this back the other way, and basically every 5 degrees Fahrenheit I will just go like this. And the next 5 degrees I'll go back the other way. And I'll do this until I get a spark that goes across the surface of the binder, and at that point we'll record the temperature. We're allowed a minimum of 230 Celsius, that is 450 Fahrenheit, in our SuperPave grading system. That is hotter than you should ever have your asphalt binder heated. Now I know things do happen, and when I say that to contractors, they laugh at me, but 230 Celsius has got a pretty good safety margin in there from normal working temperatures. This is the rotational viscosity test. This is our SuperPave viscosity test. We tested at 135 Celsius. And the reason for this test is we are making sure that at normal handling temperatures, the asphalt binder is handleable and pumpable. We can have the best binder in the world. It can be any PG grade you want it to. If it is so stiff at normal working temperatures that contractors have to do something over the top to get it through their mix plant and to get it to mix with the aggregate, then they're not going to be terribly interested in selling it. So we're just making sure that we are within a normal range of viscosity. The test is a concentric cylinder rheometer, so I have got a cylindrical sample holder. I put, for this particular spindle right here, I put 8 grams of binder in this. Put this down in the sample chamber. I will attach my spindle. This is the number 21 spindle. I will attach it just like so. Lower it down. And then I'll let it spin at 20 RPM. 10 minutes to equilibrate, and then I can just read the viscosity right off the digital readout here. We're allowed a maximum of 3 Pascal seconds for SuperPave, and if you want to get bonus points and act like you really know what you're doing, go read the fine print on AASHTO M320. There is a line in there that says if you're a supplier of asphalt binder and you've got a binder that is greater than 3 Pascal seconds viscosity at 135 Celsius, but you are still willing to certify that it is pumpable, then you can convince the DOT or whoever you're selling your asphalt to waive this requirement. So there are binders out here that we use that don't meet this requirement, but you just have to be able to certify that they are still handleable and workable.
So y'all see how busy it looks in that binder lab. There's a lot of things going on, but for this this lab report, the only binder test we want to focus on is that rotational viscometer. And she briefly touched it, but there's a better video that she's done where she's gone through the process. She's done the procedures for y'all. so that y'all can learn it a little bit more in depth. I've also wrote out some of the important things for you, but this is one of the tests that y'all will need to write out in your report specifically. The other one's not so much. So I'll touch on this. So it's ASTM D4402, standard test method for viscosity determination of asphalt at elevated temperatures using a rotational viscometer. The test is also called the Brookfield. The machine is called Brookfield viscometer. People might call it just a Brookfield viscosity test. Rotational viscometer. You can call it a few different names. And the reason why it's conducted is to determine the appropriate mixing and compaction temperatures for the binder when making hot mix asphalt. So like she said, if you can't pump it, it doesn't flow right, you're not going to want to have that binder in your mix at all, because you don't want to have to try and pump it through your plant or try and pave it down and it's not going to work with you. It's like think about trying to make a concrete slab, and your concrete is already starting to cure. It's going to be really hard to work. It's the same thing. You don't want it to be really hard to work with. So you have to do this test to figure out if it's going to be workable at those mixing temperatures, or what mixing temperatures do you want. So just a few things. Viscosity is the resistance to flow. So a high viscosity means you've got high resistance to flow, which is like honey or molasses. And then low viscosity is low resistance to flow, or water. So the viscosity of the binder can control pumpability of the binder, mixability, and workability when paving. Those are three very important things, because obviously you're going to be working with rocks and binder. So if that binder is not workable, then obviously the rocks are not going to be workable. So that's the one key to it that allows it to be workable when you're paving. And then the binder viscosity is directly affected by temperature. If your binder is really cold, room temperature, then it's not going to flow. If it's -10 degrees in that bending beam test, it's not going to want to flow. It's going to want to crack. And if you've got binder that's really hot, 170, 180 degrees, it's going to want to pour like honey. So not exactly like water, but it'll pour real easy. And if it gets over that temperature, that flash point temperature, then it will ignite, and you don't want that, because if you've got pumps or lines in your plant that are too hot and it touches that, it's going to catch fire, and you don't want that. It's a petroleum product, so you don't want it to catch fire, because that would be bad news. So for the rotational viscometer, you've got the rotational viscometer set up, little machine right here. You've got a temperature controller that controls to the 1/10 of a degree, and then you've got a heating or environmental chamber right here, which actually heats up and gets that temperature, and you can connect both of these things so that it gets to the right temperature that you need it to. And I think they allow 0.1 degrees difference in that. So if it's 135.2, that's no good. You want it to be 135 plus or minus 0.1. I'm pretty sure that's what it is. And then you need a sample chamber, which is where you pour your binder into in these little cylinders right here. You have your spindle, which is hanging. There's multiple sizes for different binders you're testing for different amounts. You need pliers to be able to grab things and pull them out, put things on, and then you need your binder, obviously. The procedure, you want to measure out 8 grams of heated asphalt binder into a cylinder. If it's not heated up, it's not going to pour, so you got to heat it up at least somewhat, and then you'll place it into that conditioning, the environmental chamber, and then that will equilibrate at 135. That's what you want to test at first. If you test at 165 first, then you're going to have to wait a really long time for it to cool down. So that's why you want to test the lower temperature first. So you'll place the sample into the spindle holder, heat it to 135 Celsius. You might have heated it to 130 prior to putting it in there. That would probably be really smart. You could even heat it to 135. So then at the temperature, you measure the viscosity until it reaches the equilibrium. The viscosity, obviously the little spindle spins and it measures it with torque and tells you what the torque is. And then it reads you a specific unit, Pascal seconds, I believe, is the viscosity reading. And so what it does is it just wants to get that torque value to the same, like you want it to sit at the same torque. You don't want it to be changing. If it's changing, then the binder is probably not to the right temperature yet. So once it's at equilibrium, then you record 3 viscosity readings 1 minute apart, and that's just so you know that you've got it in equilibrium. So you should get 3 of the same value, or 3 really close values. And you record it with 3 significant figures. And then you heat it up to 165 and repeat that last step. So you record 3 viscosity readings 1 minute apart, and then you will plot viscosities and temperature on a Brookfield plot and determine the mixing and compaction temperatures. And I will go over that after we watch this video that she has done that's a little bit more in depth.
We're going to run a rotational viscosity test, and we will use this to get your mixing and compaction temperatures to use in your lab. I'm going to go ahead and pour the sample while it's hot, and then I'll go ahead and talk about the test and the equipment. This is a 6722 asphalt binder. It has been in the oven at 140 Celsius for a couple of hours, so it's nice and runny and ready to pour. And I've stirred it up well because we stir up everything. Now I need to pour for the spindle that we are going to use. We are going to put 8 plus or minus 1/10 of a gram into one of these aluminum sample chambers. These have also been preheated at 140 C. They were in the oven with the sample. So I'm just going to go ahead and pour that. We want the whole sample in the tube, not on the sides, not running down the top. Just want everything in there. And I need another 1/10 of a gram. Let's see if we can get this. All right. So there's 8.0. Now, I will bring it over here to the thermocell unit, and we'll drop it down in here so it can start equilibrating to its test temperature. It just slides right in like so, and then we'll twist it around until it locks. And once it locks in place, it won't be able to move when the spindle's turning, because we don't want it moving while the test is running, because that'll affect our results. This is the spindle that we're going to use. This is number 21. We have 2 spindles that we use for superpave testing. It's 21 and 27. This is for very stiff materials, about a PG 76 or above is when I switched to this one. But we're going to be using this one today, so I'll go ahead and place it in here. It just connects like so. And then I will lower it down. I have height guides. Whoops, and be very careful when you're lowering it, not to bend your spindle. But I have height guides on here that tell me how far down I need to be. And then I have a centering guide that gets my spindle centered in there. If we have done everything correctly and we've used the proper amount of asphalt binder, once it is connected like so, we will have 1/8 of an inch of asphalt binder above this connection right here. All right. So this is the DV2 Plus Brookfield Rotational Viscometer. There's several models out there. You may see something slightly different if you go to somebody else's lab. They all consist of the same basic working parts, though. We've got a torque motor in the head with some digital controls. I've got a thermocell unit. This is what maintains my temperature. We're going to test our first sample at 135 plus or minus 1 degree Celsius. And then I've got an external temperature controller that actually keeps me within that temperature range. The rotational viscosity test is part of the Superpave performance grading system. We run it at 135 C when we're grading our asphalt binders. It tells us that the asphalt binder is handleable, workable, pumpable at normal mixing temperatures. And have the best binder in the world, meet any PG grade you want it to. If it's so stiff and nasty and unworkable at normal temperatures, then nobody's going to want to buy it. So we're allowed a maximum of 3 Pascal seconds at 135 Celsius. And again, that's just to ensure that we can actually work with this material. For the test, once I've got everything together, I'm going to let it get back up to temperature. I've got my digital readout right now set to percent torque. My speed is 20 RPM. That is what's required for SuperPave. We rarely vary off of that. And I can hit motor on, and I'm going to watch this percent torque. I want to make sure it doesn't go above 98%. If it does, I need to turn the machine back off because I'm going to break my torque motor. Usually, if that happens, I can just wait a couple minutes and try it again, and it'll be warm enough to run. If I've got a sample I just can't get below 98%, then that is when I would pour a new sample and switch to this little guy. But we went up to 32 or so, and now it's coming back down. So this is good, and I can go ahead and hit select display. And I can read my viscosity and centipoise right off the digital readout here. The other readings here, I've got spindle number, that is 21, this is 27. The spindle number tells the machine basically what spindle it has, what's its size, what's its weight, diameter, whatever it needs to know to do the viscosity calculation. So this is spinning at 20 RPM, and we right now have to leave it to equilibrate for 10 minutes. This has been spinning for about 10 minutes now. We are required a minimum 10-minute equilibrium time. So I'm going to take my first reading. It's going to be 570 centipoise. Now we need to report in Pascal seconds. We just divide by 1,000. So I'm going to write down my first reading as 0.570 Pascal seconds. And this is at 135 Celsius. I'm also going to check my percent torque just to make sure that we are still within tolerance. And we are at 22.8. We are allowed to be between 10 and 98% torque. Well, I've already talked about the 98%. Below 10%, then the sample is so liquid at that temperature that we're not getting a lot of resistance to the spindle turning, and we are just getting noise, basically. So we are valid on our torque, 22.6. And I'll go back to select display. Our test results, we write down 3 readings. We wait 1 minute between each of them. This lets us know that we are fully equilibrated. If the results are still going up or down or bouncing all around, then we kind of need to wait a few more minutes and figure out what's going on, see if we can get it to stabilize. So it's been a minute, and we'll take our second reading, 0.570. So far, so good. And again, this is Pascal seconds. And we'll wait 1 more minute and take our third one. And 0.570. So I'm going to write down for my viscosity at 135C, it's 0.570. For mixing and compaction temperatures, we need to get a range of results. So I'm going to do 135C because I have to do that anyway for SuperPave grading, so I might as well kill 2 birds with 1 stone. My second temperature, I'm going to use 165C because I know it works for this binder. And so I'm going to go over here and change this. And now we'll wait and let that equilibrate. Leave the sample. We can run the same sample, still 20 RPM. I don't have to turn it off. It can just sit here and spin for the equilibration time. But this will take a couple of minutes. These are very small samples. This thermocell unit is very good. It heats up pretty quickly. We have equilibrated at 165 Celsius. We're going to take our first reading. It is 165 centipoise, so that is 0.165 Pascal seconds. And same as before, we will wait a minute between each reading. 0.165 for the second one. And we'll wait 1 more minute and take our final reading. And 0.165 for an average of 0.165. Both of these are well below our 3 Pascal second maximum that we're allowed in SuperPave. So this binder should have absolutely no problems for SuperPave grading. If you do have a binder that fails that 3 Pascal second maximum, go look at the chart, the AASHTO M320 chart. Read the fine print. There is actually a note in there that says if you have an asphalt binder that is greater than 3 Pascal seconds at 135 Celsius, and you as the supplier of that binder are willing to certify that it is pumpable, then you can possibly get that requirement waived. So it's not a set in stone requirement. There is an out if you fail it, because we do have binders that we know based on the way they're made, they are very stiff, but they're still very workable. So that's in there for those binders. Now I'm just going to turn this off and we are done.
All right, so pretty easy test out of all the others that you can do. So this is what the Brookfield page would look like. We would typically give y'all each one of your own sheets that has all this stuff on it minus the lines. And so I just wanted to show you this quick example. If your sample was at 50C, your viscosity would be really high. There'd be a high resistance to flow, so it'd probably be up here close to 100 Pascal seconds. And then if your binder is heated up, it's slowly going to increase, or it's going to actually, the viscosity is going to decrease as the temperature increases indefinitely. But what we need, there's these compaction range and mixing range. This is provided on that Brookfield chart. So what we do is we just plot our points. So we use the log scale in Pascal seconds and a log scale in temperature. You can see this is a log scale, or see starting at 100 and it goes on, but this is zoomed in quite a bit. But what they do is they provide a small compaction range for viscosity, because we want compaction viscosity to be this certain amount, certain Pascal seconds, because then we know that it's going to be workable. We don't want to say, hey, our binder has to be exactly 155 degrees for compacting, because each binder is going to be different. So if they provide a viscosity for us to try and reach, then we can say our temperature needs to be this, at whatever temperature this is right in here. And then our mixing range when we're at the plant, it is going to be a little bit higher. So this one looks like it's about 155 or so. And so there's a range provided for this. So in your report, you won't need to make this whole graph. The only thing you need to do is to report the temperatures for mixing down here and compacting. And those temperatures, let's see if I got some animation here. So our compaction temperature is actually 145 to 149 degrees Celsius. So we get those two readings, report those in our lab report, and then our mixing range is 156 to 162 for what we did. So those two values right here, that's what you need to report in your results. Obviously, in methodology and the scope, you need to write out the rotational viscometer procedures and such. But in the results, you just need to provide this. You don't need to provide the whole graph. Don't screen cap it. That's not what you need. Just these two things. So we'll move on to the actual beginning of our HMA stuff. It's the batching of it. So we've already done our binders. And next we're looking at the aggregate. So our aggregate, ours specifically, it got changed, I think, a year and a half ago because we ran out of material. So we had to go get new material to use, and we had to do a new mix design for it. But this one right now, we have sand, which comes from Shorter, Alabama. And then we have granite, that's number 89 gradation, and M10. So these are just gradations that are provided that different contractors might say, hey, can I get, you'll have a stockpile of 89 granite, and they'll say, sure. And that's just some specific gradation of it, same as M10. So the limestone M10 and the granite M10 are both the same gradation, but they're different materials. They're different rocks, different aggregates. So we have 4 different aggregates in our blend completely. The equipment you need to batch, very simple. You just need a balance or a scale. You need 4 pans. You need a flat bottom scoop. You need 3 large cans, 2 large, 1 small. We actually would use more. When you would do this in the lab, each group of like 3 or 4 people would do 3 cans. But I could technically have written out 12 because we're going to have multiple different samples we're going to make. So the procedure, you place each aggregate type in separate pans, about 1 kilogram more than you typically need. That way you don't run out of material. It's just easy to do it like that. Then you need to homogenize the aggregate so there's no segregation occurring. You can just toss it with the scoop and just mix it up. And then you'll scoop from the bottom of the pans, collecting a representative sample of the aggregate. You want to scoop from the bottom because if you scoop off the top, you might just get some of the coarser aggregate that hasn't fallen through the other aggregate. If you scoop from the bottom, you're getting a good representative sample. And I'll show you that in the video. And then also you want to weigh out your portions of each aggregate to fill in the cans. And then the portions you need, this comes like directly from what you would have seen, is the batching sheet. So for our asphalt sample we want 36% granite, that's the number 89. You want 18% of limestone, 18% of the granite M10. See, both those are the same. They're just different aggregate sources. And then you want 28% sand. So that's the one that they've come up with. And that obviously comes to 100% of the aggregate. And then we've got the weights. So this is our large sample, 4,650 grams, and this is our smaller sample, 1,500. So it just tells you in grams what you need. And we're going to do 2 compacted samples, 2 large ones, and then 1 small. You'll learn what the rice is. That's where we just figure out our maximum theoretical specific gravity. And the compacted samples are just like black pills of asphalt. So the next video is the last video of today's lab, but it's just the process of batching.
So now we're going to do some batching for our asphalt. Asphalt's comprised of a lot of different aggregates. We have 4 different aggregates that we're using for our mix design. And so we have samples we're going to make. We're going to make 2 identical large samples and 1 smaller sample for other tests you all will see in later weeks. And so we have a batching sheet here. I'm going to show y'all what it looks like. So we've got our 4 aggregate types and the weights for each of those. The G&B is our large sample, ends up being 4,650 grams. The small sample is 1,500. So our 89 granite is this one right here. It's pretty coarse. It's not as big as that limestone that we tested in previous labs, but it's still the coarse aggregate that we're using for ours. And the 89 is just the grade that it has. So if you go to a plant, they might have 89 in limestone, and it's based on that size and this gradation. So that's how they specify it. Shorter sand, this is just sand here. I guess shorter is where it comes from. So we will need 1,302 grams for the large and 420 for the small. Then we have our M10 granite. Again, M10 is just the gradation of it, so it's pretty fine. But it does it's kind of a variation of different sizes in there. And then the limestone of that is M10, and it's the same thing. It's just limestone, not granite this time. So it's got some dusty particles in it and some coarser particles in it, but not too big. So what we'll do is we want to weigh out these samples according to that sheet. So I will first start by turning on my scale and zeroing out my 10 until it hits 0. There we go. All right, so now I want 1,674 grams for granite. So the way you do this is you don't want to just scoop off the top. If you scoop off the top, then you're not getting the full sample because smaller particles could fall to the bottom underneath these coarse ones. That's what segregation is. So what you want to do before you scoop anything is you want to mix it up together as much as you can, homogenize it. So I'll do that real quick. So you want to scoop it up and flip it. You want to toss it together in itself. So now that we've done that, I want to get a nice big scoop. You see I'm using a flat scoop. That way I can get any fines on the bottom because we want to get a complete sample. We don't just want one size of this stuff. So I'll scrape from the bottom and then I'll dump it into here and see if I can hit 1674. So see, I did a nice flat scrape on the bottom. Okay, so that was too much. A little bit less. So now I'm pretty close, but what I'm going to do, try and scoop out some. There we go, 1674.2. So it is not the best to use your hand to take it out, but when you're trying to get a sample, you're not always going to get it perfect. It's going to have some segregation in it. So now we've got that 1674. Let me re-zero it. And now I need to add in 837 grams of M10 limestone. So same thing. Here we go. I gotta flip it and toss it around. All right. So now I need 837. I think that's probably pretty good. I hope that this fits. Actually, you know what I'm gonna do? I will use this right here, just in case I mess up, because I don't want to put too much in there. Oops, that's too much. So now, $837 is what we're trying to hit. Here we go, 837. Now we'll put this sample in here. 837 for M10 granite. We'll flip it. It's too much, but that's okay. We'll see what we can do. There we go. And then the last one is our sand. We need 1,302. So sand doesn't really segregate. It's all kind of the same size, but we can still toss it. All right. Let's see. I think that should be good right there. Woo! 1,302. So take off a little bit more. All right, 1,302.3. Close enough. All right. So that's our large sample. We'll do the exact same thing for our second sample, and then for the smaller one, you just follow the same thing. It's based on percentages. So 36% granite, 18% limestone, 18% M10 granite, 28% sand. So it's just based on that, and we'll come up to the same thing in a smaller tin, and that's used for a different test. So that is how we do batching.
So pretty simple. Really easy procedure of just filling rocks into a can. So next week we'll get into the mixing and compacting. This is actually what an asphalt pill looks like after we compact it. So it's got a certain amount of binder in there and then all the aggregate that we made. So let me go ahead and end this, and then I will ask y'all if there's any questions.